Hi everyone, this is going to be the first lesson on the topic of organic chemistry for GCSE chemistry students. In this lesson we're going to be taking a look at crude oil, how it forms and how it can be separated into fractions which can then be used to make useful products. Now we're going to be expanding upon some of the ideas that we encounter in this lesson, but to start with, let's take a look at the learning objectives for this lesson. So once you've completed watching this lesson video, and also once you've completed the various questions that will pop up at various intervals in this video if you're watching it on my website, together with the end of lesson quiz and the exam questions, which will be in your downloadable pack of exam questions for this topic, you should be able to do the following things. So in this lesson, we need to first start by looking at crude oil. Now, crude oil is a mixture. It's a very complex mixture of hydrocarbons, and we're going to be exploring the idea of hydrocarbons both in this lesson and subsequent lessons of this topic. And we're going to be looking at crude oil in the sense of how it is formed. It's a natural substance. It's often referred to as a fossil fuel. Now, that's not to say that any fossils have ever been found in crude oil. It's made from, over long periods of time, from the decaying remnants of deep sea microorganisms and also living organisms that were in the sea, which have decomposed over long periods of time under conditions of high temperature and pressure. We also need to look at the importance of crude oil. Now, if you were to go back before the discovery of crude oil and the development of organic chemistry as a result of that, and you looked around the average home at various objects and items in the home, you'd find that they were almost all made of natural materials, things like stone, wood, metal, and also animal products, things like leather, and also plant products such as cotton fibers. But nowadays, so many of the items that you find around you are made from the substances that we get from crude oil, things like plastics and also pharmaceuticals, and an unimaginable different variety of different substances. So modern life and the modern standard of living and many aspects of modern technologies are entirely dependent upon crude oil. Now, I haven't yet mentioned the idea that many of the fuels that we burn, both to produce electricity and also in fuels used in vehicles, are derived from crude oil. So crude oil has an enormous importance for the modern world, and we're going to be looking at that in this lesson. We then need to go on to look at how do we separate this very complex mixture of substances, this crude oil, into useful substances and useful fractions. This is the process that we refer to as fractional distillation. So we're going to be looking at that, and we're going to start by looking at hydrocarbons in this lesson by exploring how they differ in their physical properties and how this depends upon the size and also the shapes of the molecules of those hydrocarbons. We also need to look at the simplest kind of hydrocarbons, the alkanes, and to look at the concept in organic chemistry of a homologous series. And we also finally need to look at some of the uses of the fractions of crude oil, such as gases used in domestic heating and cooking, such as methane, all the way through to the larger molecules found in fractions, which are used to make things like fuel oils, and bitumen, which is used for surfacing of roads and roofs. So there's quite a bit to get through in this lesson, and as always, I'm joined by a lot of students via Zoom. Many of you, again, have asked a number of very important questions that I will be addressing through the recorded segments of this lesson. Some of those questions I'll be addressing in the Q&A session that will follow the recorded segment of this lesson. So those of you in attendance, keep those questions coming in the Q&A box, and I'll answer those towards the end of the lesson in the order in which they receive votes. Now, if you're watching this as a recording, as always, if you have any questions, you can simply log into the website, navigate to this lesson's page in the GCSE chemistry course, and you can either leave those questions as comments in the live chat, in which case you'll start a discussion with other students and I'll respond there. You also have the facility to send me a private message with your questions, in which case I'll respond to those privately within about 24 hours. And if you're watching this elsewhere, such as on YouTube, then as always, you can type your questions into the comments and I'll get back to you there as well. Okay, so let's make a start then. So let's take a look at how crude oil arises, where it comes from. So millions of years ago, the dead bodies of tiny marine animals, microscopic and also macroscopic animals and plants, formed a thick layer of sediment on ancient seabeds. Now, over the course of time, this layer of organic matter became buried under a heavy deposit of mud, sand, silt, and rock fragments. So here we have the organic matter steadily being buried under an increasingly thick layer of material here. So, over long courses of time, under the influence of heat and pressure from the overlying layers of rock, the organic remains will partly decay over millions of years, and this forms a pocket eventually of both crude oil and also natural gas. The gas and the oil tend to collect beneath layers of non-porous rocks. Now, in the 20th century, we learned how to extract this oil and also the natural gas from the geological strata and began to exploit it on a massive scale. Today's oil industry is now worth trillions of dollars as a result of this extraction and exploitation of these natural resources. So crude oil is a natural, non-renewable resource. Eventually, all the oil reserves of the world will be used up, and part of the reason for this is all of the different uses that we've found for crude oil have led to this enormous demand for crude oil. And at this point in time, it's being extracted much more rapidly than it's being formed. Again, crude oil forms over millions of years, and we extract and use many billions of tons of this substance over the course of just the 20th century, never mind the increasing demand and the increasing use that it's going to be put to in later centuries. So here we see an oil extraction platform where the oil is being extracted from under the seabed. And typically gas and oil, natural gas and oil deposits are usually found together. So you also find typically in close association with the oil extraction platforms, you also find natural gas platforms as well. Now, crude oil can also be extracted from terrestrial sources on land, where it's found deep under the ground. So here we see this device here. This device is actually called a donkey because it does resemble a donkey, as you can see here. And so it's actually just a pump, which is being used to pump crude oil from deep within the ground up to the surface, where it can then be stored and then transported. Now, speaking of the transport of crude oil, oil is often carried by very, very long pipelines, and typically it's being delivered either to a ship, a container ship, or to a refinery where it can be separated into fractions, as we'll see a bit later on. So this oil pipeline that you're seeing here is in Alaska and is over 800 miles long. Now, over 420 miles of this is elevated above ground level. So you can imagine just the amount of the cost involved in maintaining these pipelines. Now, this is still economically viable because of the enormous value that crude oil has. Now, oil can also be transported by container ships, typically very large ships, to oil refineries. What you see here is an oil refinery in North Lincolnshire. Now, the refining of crude oil is so economically important that typically oil refineries will operate 24 hours a day, 7 days a week, 365 days a year. So I've already mentioned that crude oil is a mixture. Now, going back to the topic where we talked about structure and bonding and the classification of materials by chemists, matter can be categorized as either being pure substances, which are either elements or compounds, or mixtures of different pure substances. Now, crude oil is a very, very complex mixture. Now, in a mixture, the different components of that mixture, whether they're elements or compounds, are not chemically bonded to each other and can be in any proportion. So a mixture, because it contains the molecules of different substances, does not itself have a chemical formula. Instead, we describe mixtures in terms of formulations. Now, the word formulation simply means a list of all of the different substances in that mixture and their relative proportions. So mixtures obviously are very different from compounds. Compounds are substances containing two or more elements that are chemically bonded to each other in fixed proportions. So crude oil is a mixture of compounds referred to as hydrocarbons. Hydrocarbons are compounds composed only of carbon and hydrogen atoms. Now, the simplest hydrocarbon is methane. So here we can see a ball and stick model of methane. The black atom here represents the atom of carbon, and we have 4 atoms of hydrogen chemically bonded to that single atom of carbon by single covalent chemical bonds. So hydrocarbons are compounds composed only of carbon and hydrogen. So here we can see methane, a ball and stick model. Now there are 3 main categories of hydrocarbons. There are alkanes, alkenes, and alkynes. Now each of these is a category of compounds. Alkanes are a type of hydrocarbons containing only single carbon-to-carbon bonds. Now, in the case of methane, this is the simplest alkane. It only contains 1 carbon atom. But there are other alkanes containing 2, 3, 4, 5, and more carbon atoms bonded together. And so organic chemistry becomes incredibly complex because of the nature of carbon. Carbon, unlike other elements, can form very stable, very strong single bonds to itself. Now, as you've already encountered, all of the elements in the same vertical column, in the same group of the periodic table, typically will share similar chemical properties. Now, even so, carbon can form much more stable single bonds to other carbon atoms than silicon can to other silicon atoms. What this means is that molecules which are based upon the chemistry of carbon can grow very large and very complex. And so, for example, biological organisms, which are the most complex systems essentially known to science, are based upon building blocks, molecules such as proteins, carbohydrates, lipids, nucleic acids, which are incredibly complex when compared to other simpler molecules found in non-living systems. Now, the reason why living organisms can grow so complex is because their building blocks, their molecules, are themselves very, very complex and very large. And this is made possible by the fact that those building blocks, those biological molecules, are based upon carbon atoms forming stable single bonds and double bonds and triple bonds with themselves and with other atoms of other elements. So, organic chemistry is the branch of chemistry that deals with carbon compounds, and because of this ability of carbon to form very, very strong, stable bonds with other carbon atoms, the branch of chemistry that we call organic chemistry deals with both very simple organic compounds, the simplest of which being this one, methane, and much, much more complex ones, such as the ones found in biological organisms. Now, there will be another lesson on polymers, synthetic polymers and biological polymers later on in this topic. But the understanding of organic chemistry begins with an understanding of the simplest type of organic compounds, which are the alkanes. So alkanes are hydrocarbons, alkenes and alkynes are also hydrocarbons, but alkanes are based upon alkanes are hydrocarbons which only contain single carbon-to-carbon bonds and hydrogen atoms. So the simplest would be a molecule containing a single carbon atom bonded by individual single bonds to 4 hydrogen atoms, and this is what we see here. Now, these are all examples of homologous series. Now, if you think about what the word homologous or what the word series means in maths, it's a sequence, essentially. When we talk about a series in maths, it's a sequence of numbers. And it's the same principle when we talk about organic chemistry. So let's have a look here at the first homologous series. So the term homologous series this essentially refers to a group of compounds which have the same general formula. And we'll see what that means in a moment. Same general chemical formula. Where each member of the series differs from the previous member by a unit of CH2. So let's take a look at what this means for alkanes. So alkanes are the simplest homologous series. So we've already seen methane. Methane has a single carbon, singly chemically bonded by covalent bonds to 4 hydrogen atoms. And so this is what we would refer to as the displayed structural formula for methane. A displayed formula is a representation of one molecule of a substance where we see all of the atoms and all of the bonds represented as a diagram. So this would be the displayed formula for methane. The molecular formula for methane would be this, CH4. A molecular formula is an expression that describes the exact numbers of atoms of each element present in one molecule of that compound. So we have a displayed formula here, and we have the molecular formula here. So this is referred to as methane. So we see here the suffix on the end of this name, ane. This refers to the fact that this compound belongs to the homologous series, the chemical family of compounds that we call alkanes. So all alkanes end in the suffix ane. Now meth, as we'll see, is a prefix used in organic chemistry which refers to one carbon atom. So this is methane. Now the next member of the homologous series of alkanes looks like this. We have 2 carbon atoms. Because it's an alkane, alkanes are distinguished from other homologous series of hydrocarbons by only containing single carbon-to-carbon bonds. Now obviously in methane we only have 1 carbon atom, so there can be no carbon-to-carbon bonds, but in this one we have 2. And the remaining bonds are to hydrogens. So this would be the next member of the homologous series of alkanes. So this is the displayed formula. It shows all of the atoms and all of the bonds in one molecule of the substance. So the molecular formula for this one would be C2H6, 2 carbons, 6 hydrogens. Again, the molecular formula of a substance shows the exact numbers of atoms of each element, in this case carbon and hydrogen, found in one molecule of that substance. This member of the homologous series of alkanes is referred to as ethane. So again, we have the suffix ane that tells us it's an alkane. Now the prefix eth in organic chemistry means that whatever molecule you're dealing with has 2 carbon atoms in it. So this is ethane. Now the next member of the homologous series of alkanes is this one. 3 carbons, all bonded singly to each other, and the remaining bonds around these atoms are all to hydrogen. So this would be the displayed formula of the 3rd member of the homologous series of alkanes. So here we have the 3rd member of this homologous series. So we see here that this one has 3 carbons, so its molecular formula will be C3, and it has 8 hydrogens, H8. This is the molecular formula, and this is the displayed formula of propane. So again, we have an ane telling us it's an alkane, and we have the prefix prop. Prop means 3 carbons. So whenever you see prop in the name of an organic substance, it means 3 carbons. If we look at the next member of the homologous series, we have 4 carbons, and the remaining bonds again are to hydrogens. And I'm not going to draw all the hydrogens in place, although in an exam, if you were to draw them displayed formula, you must show all of the atoms and all of the bonds. I'm not going to draw them just for the sake of time here. But so we see here we have 4 carbons, and in this case we have 10 hydrogens. So this would be the molecular formula, and this is butane. Again, we have ane, which means it's an alkane, and we have the prefix but, which in organic chemistry means we have 4 carbons. Now there are other members of this homologous series. There is the next one would have 5 carbons. Oh, not sure why it switched to blue here. Let's go back to this one. Let's get rid of this. So we have 1, 2, 3, 4, 5 carbons, and the remaining bonds are to hydrogen atoms, which I'm not going to draw again, just in the interests of time. So we see here this one is C5H12. This is going to be pentane. So ane for an alkane, pent meaning 5 carbons. Now we have other members of the series, which are going to be hexane, heptane, octane, nonane for 9, decane for 10, 11 would be undecane, and so on. But these are the ones that at the bare minimum you need to know. Now notice all of these have the suffix ane, which indicates that they're all members of the homologous series of alkanes, and the prefixes indicate the number of carbons. So we have hexane, 6 carbons. If we were to draw this out, we would find that it would have 14 hydrogens. Heptane, 7 carbons. If we were to draw that out, we would find it would have 16 hydrogens. Octane, C8. If we were to draw that out, we would find that it would have 18 hydrogens. Nonane, 9 carbons. If we were to draw that out, we would find that it would have 20 hydrogens. Decane, C10. Again, if we were to draw that out, we'd find it would have 22 hydrogens. So we see here, in keeping with the definition of a homologous series, each member of this homologous series differs from the previous member by a unit of 1 carbon and 2 hydrogen atoms. So to get from methane to ethane, we extended this carbon chain by 1 carbon, which is bonded to 2 hydrogens. To get from ethane to propane, we added another CH2 here. To get from propane to butane, we added another CH2, and so on. So what we see here is the homologous series of alkanes. Now, if we look at these, we could write a general formula. Which describes all of these members of the homologous series of alkanes. So if we have n hydrogens or n carbons in our molecule of an alkane, the number of hydrogens that we have is always going to be 2n plus 2 for these linear alkanes. Now, by linear, I mean that these are molecules with a straight single chain of carbon atoms. So this is the general formula for linear alkanes. So again, in keeping with the definition of a homologous series, they all have the same general formula. They all have carbons and hydrogens in the same general proportion. Now, I mentioned linear alkanes. There are such things as cyclical alkanes. So for example, this is linear butane, but we could also draw a butane molecule with 4 carbons arranged in a ring. Now, because carbon can only have 4 single bonds around it, this carbon has 2 single bonds, so the remaining 2 bonds are going to be to hydrogen atoms. So same thing for this carbon here, and the same thing for the other 2 carbons in this ring. Now, as you'll notice here that this version, if you like, of butane, this cyclical version of butane, actually has a different molecular formula. We have C4H8. So this is referred to as cyclobutane. It's an alkane, it's 4 carbons, and it's cyclical. So you can see here that there is a specific systematic way of naming hydrocarbons, and also in organic chemistry there is a systematic method of naming the compounds depending on the arrangement of atoms, the numbers of atoms, and what types of bonds are present. This allows organic chemists to use a single naming system or nomenclature to describe all organic molecules. And in theory, if you know that system well enough, you should be able to draw the displayed formula of any organic substance once you know its name. And conversely, if you see the displayed formula of an organic substance, you should be able to write down its name by making use of that same system. Now, if we're looking at this one, if we also draw, for example, the displayed formula of cyclohexane, cyclohexane would look like this. 6 carbons arranged in a ring, and this means that, and I'm not going to draw all the hydrogens, the remaining bonds around each of these carbons are all going to be to hydrogen atoms. So the molecular formula of cyclohexane is going to be C6H12. So we see here that for cyclical alkanes, the general formula is slightly different. The general formula for cyclical alkanes, cyclic alkanes is going to be CnH2n. So this is the general kind of naming convention that you start with when you're learning organic chemistry. We've just looked at the simplest type of organic compounds, the hydrocarbons. But there are two other homologous series of hydrocarbons. There are the alkenes and there are the alkynes. So let's take a look at alkenes and alkynes. And again, we're going to be coming back to these in later lessons. So alkenes are a homologous series which are distinguished from others by the fact that they contain the carbon-to-carbon double bond. So alkenes. So the simplest alkenes are a homologous series, and they all, somewhere within their molecules, will contain one or more carbon-to-carbon double covalent bonds like this one. So the simplest alkene, the first member of the homologous series of alkenes, is going to be this one, because in order to have a carbon-to-carbon double bond, you need 2 carbon atoms at the very least. So this would be the first member of that series. And again, it is a hydrocarbon. It contains only carbon to hydrogen atoms. So the molecular formula of this is going to be C2H4. This would be its displayed formula. And again, a displayed formula shows every atom and every bond in the molecule as a diagram like this. So this is named ethene. So here we see a different suffix, ene, and whenever you see this, you know you're dealing with an alkene. And as we saw before, eth as a prefix means 2 carbons, and we can see that here. Now the next member of this series is going to be an alkene containing 3 carbons. So we have 3 carbons, and we have between 2 of those carbons a double covalent bond. So this one is going to look like this. The remaining bonds are all going to be 2 hydrogen atoms. Now, this carbon has a double bond, so it can only form 2 bonds to hydrogen atoms. This carbon here has 2 bonds here and 1 bond here, so the remaining bond is to a hydrogen atom. So this is referred to as propene, prop for 3 carbons, and ene because it's an alkene. So the formula for this is going to be C3H6. We could continue this. So for example, we could have butene, 4 carbons, and it's an ene, so it's going to have a double bond here. Now in this case, I draw in the hydrogens for this one. So here we see butene. It has the molecular formula C4H8, 4 carbons, 8 hydrogens. Now, in this case, again, we see but, which means 4 carbons, and we see the suffix ene, which means it's an alkene. However, if you pause to think about it, there are 2 ways that if we were given the name butene and the molecular formula, there are 2 ways that we could draw this alkene. We could either draw it like this, or we could draw it like this. We could put the double bond instead between the 2 central carbon atoms like this. Now both of these are butene, but they are different molecules. So this one here also has the molecular formula C4H8. So this is also C4H8. Both of these are versions of butene, but they are different. Now, an organic chemist, again, it uses a systematic naming convention from which you should be able to draw the full displayed formula if you're given the name. So how do we distinguish between these two in terms of their nomenclature, in terms of their naming? Well, this is where we get to the next level of our understanding of organic nomenclature. First of all, We've already identified that these prefixes in the names of these organic compounds, eth, prop, bute, and so on, refer to the numbers of carbon atoms. So in both cases, this is going to be a butene because there are 4 carbons present, and in both cases, it's an ene because there's a double bond present between 2 of the carbons in the molecule. So the next step is to identify the longest continuous chain of carbons, which we've done, and then number that chain from the end nearest what we call the functional group. Now, the functional group in alkenes is the carbon-to-carbon double bond. The term functional group is something that we're going to be coming back to later on. Functional group in organic chemistry means a group of atoms within a molecule which is responsible for the characteristic chemical properties of that molecule. So in alkanes, if we go back to our alkanes, the functional group was the carbon-to-carbon single bond. So in alkanes that we looked at here, the carbon-to-carbon single bond is the actual functional group. This is the group, the functional group, this is the arrangement of atoms and the bonding between them that distinguishes alkanes from others and gives them their chemical properties. When alkanes chemically react, typically it's because of the breaking of the carbon-to-carbon bond. Now, alkenes, on the other hand, are given their characteristic chemical properties by the presence of a carbon-to-carbon double bond. So in this case, the functional group is the carbon-to-carbon double bond. So when we're naming these two, we need to distinguish between the position of the functional group as being different in these two versions of butene. So the way that we do that is we number the longest continuous chain from the end of the molecule nearest the functional group, which is, in this case, this end of the molecule. So this is carbon 1, carbon 2, carbon 3, carbon 4. In this case, it doesn't matter which end we number from. If I number from this end, then the nearest carbon, which is double bonded, is going to be carbon 2. If I number from this end, then again, it's carbon 2. So I'm just going to number from this end, 2, 3, 4. So the way that we name these to distinguish their difference in structures is by calling them like, naming them like this. This molecule here is but1 ene, and this molecule here is but2 ene. So here we see there is a number in the middle of the name which tells us the position of the ene, the position of the double bond between the two carbons. In this, it is located on carbon 1, between carbon 1 and carbon 2. In this molecule, it's located between carbon 2 and carbon 3. Now, when we do this in the name of an organic molecule, we always separate letters from numbers by a hyphen, like this. And so this is how we name these two. These two are referred to as isomers of butene. Now, the term isomer in organic chemistry means compounds with the same molecular formula. As you can see here, they're both C4H8. And different structural formulae. So we see here these two displayed formulae, which are a type of structural formula. The word formula in chemistry, when it's being applied to molecules, is in general, the word formula means an expression which tells you about the numbers and types of atoms and how they're bonded. Now, a structural formula gives you information about how those atoms are bonded to each other. A molecular formula doesn't do that. It just tells you the relative numbers of atoms of each element. So, since both of these are a type of butene, they have the same molecular formula, but they do have different structural displayed formulae because of the difference in the way those atoms of carbon and hydrogen are bonded to each other. So we have two isomers of butene which are distinguished from each other in the position of the double bond. Now, there are many more examples of this type of nomenclature or naming of organic compounds in the lessons that will follow, and also in the end of lesson quiz questions throughout this topic, as well as the exam questions which you downloaded as part of your downloadable pack of exam questions. So we see here that there are many different alkenes, and again, they differ from each other. So this member of the homologous series, propene, differs from the previous one by a unit of CH2. So we've added one carbon and two hydrogens in going from ethene to propene. When we go from propene to butene, again, we have increased the number of carbons by 1, and we've increased the number of hydrogens by 2. So this is the homologous series of alkenes, and the functional group here is the carbon-to-carbon double bond. Now, there is another type of hydrocarbon, another homologous series of hydrocarbons called alkynes. So alkynes, the functional group in alkynes is the carbon-to-carbon triple bond. So whenever we have alkynes, somewhere within that molecule you have a carbon-to-carbon triple bond. So the simplest type of alkyne contains two carbons which are triple bonded to each other, which means the remaining bond from each of those carbons is to a hydrogen atom. This is ethyne. So here we have "-ine" as the suffix. This means that we're dealing with an alkyne. And we have "eth", which tells us that there are two carbons present. So in this case, the molecular formula is C2H2. So we can go on to build up more members of this homologous series of alkynes. So here we see this is propyne here, Propyne, propyne, 3 carbons, prop, ine meaning it's an alkyne, and here again we see that we have differed from the previous member of this homologous series by a unit of CH2. So the molecular formula of this one is going to be C3H4. We can go on to butine. Oh, beg your pardon, there's no nitrogen there. It should be a carbon. So this is a carbon, and we have a hydrogen here, and we have the remaining bonds to hydrogens here. So we can see here that this is butine. And once again, if we look at the molecular formula for butine, again, but meaning 4, ine meaning an alkyne, this is going to be C4H6, and so on. So you can see the naming convention at work here. And this is, again, your kind of first introduction to organic chemistry and the way that we name these compounds. There's going to be a lot more of this in the lessons which follow in this topic. Now, I mentioned that crude oil is a very complex mixture of different hydrocarbons. Now, the vast majority of the hydrocarbons that you find that make up crude oil are alkanes of varying different lengths. Some of them are branched. In other words, rather than just having straight chains of carbons like the ones that we showed here, some of them have branches. So an example of that would be if you imagine this hexane molecule having a branch here and then another carbon and then another chain of carbons here. But the majority of the substances that make up crude oil are alkanes. Now, different substances, different pure substances, are going to have different physical properties depending on the nature and the strength of the bonding between the molecules in that substance. So let's take a look at the physical properties of some of the alkanes to illustrate this point here. Let me just expand this a bit so you guys can see it a bit more clearly. So here we have the list of the homologous series of alkanes. We've got methane, ethane, propane, butane, and so on. We have their molecular formulae. And so what we're describing here are different substances with different sizes of molecules, but they all belong to the same chemical category, alkanes. Now let's take a look at their melting points first of all. You can see here that methane has a very low melting point and also a low boiling point, so it's a gas under standard or room temperature conditions. But as we go down this list of alkanes and the molecules get larger and larger and larger, we see that the melting points increase and also the boiling points increase, so that by the time we get to pentane, pentane is a liquid at room temperature. And we see that as we then go from pentane to larger and larger alkane molecules, we see that the density of those liquids increases. So how do we explain this in terms of what we know about the molecules themselves? Well, again, this goes back to the principle that we discussed in the topic on structure and bonding. All of the alkanes are simple covalent molecules. So let me just bring up our list of alkanes again here. So we see here that these are all simple covalent molecules. They do get larger, but they are simple covalent molecules. So when we're talking about alkanes, if we take, for example, methane, the molecules are very small. Now, the smaller the molecules are, the weaker the intermolecular forces will be between those molecules. If we take a larger molecule such as pentane, and I'm just going to draw it as a kind of diagrammatic method rather than drawing the structural formula here. So if we imagine pentane molecules being larger and longer, because the molecules are larger and they can come closer to each other and have more of the molecules in close proximity to each other, the intermolecular forces, the forces of attraction between molecules in pentane, are stronger. This means that more energy is required to overcome those forces during melting and boiling, and so pentane melts and boils at a higher temperature than methane does. So the larger the molecules get, in general, the stronger the intermolecular forces become, and therefore the higher the melting and boiling points become. Also, the larger the molecules get, the greater the amount of mass there is per molecule, and therefore the greater the density is going to be of that substance, density being the amount of mass per unit of volume. And so typically, as we get to the liquid alkanes, the larger ones tend to be more dense, and this in turn means that they are more viscous. They are thicker liquids the larger the molecules get. And again, if we imagine comparing pentane to a larger alkane molecule such as decane, for example, decane molecules are larger, and therefore, again, the forces between them are much stronger than they are in pentane. This means that as a liquid, these molecules have a harder time sliding over each other when the liquid flows, because the forces between them are stronger. And so typically, as molecular size increases, and this essentially means as the relative formula mass of these substances increases, we see a trend in the physical properties. First of all, you get a increasing melting point and boiling point. You also get increasing density. If you're dealing with liquids, you get an increasing viscosity. Viscosity is a measure of the thickness, if you like, of a liquid. The more viscous a liquid is, the less easily it flows. So viscosity increases with increasing molecular size. Now, what you also find is many of these alkanes are highly flammable. Typically, the smaller ones, the ones with lower molecular mass, are much more flammable. They ignite much more easily. So if you imagine the difference in setting fire to methane. Methane is the main component of natural gas. So when you open a Bunsen burner in the laboratory, you open the gas tap, it's mainly this substance, methane, which comes out. And as we saw in that table, methane is a gas, and it will ignite very, very easily. Now, as you go further down and you get these larger molecules, pentane is a liquid. It is flammable, but it's much more difficult to ignite than something like methane. If you go further down to decane, decane is a liquid. It will burn, but it doesn't burn very well. It doesn't ignite very well. It doesn't burn very efficiently. So we can say that with increasing molecular size among the alkanes, typically you get lower flammability. So all of these are a consequence of the increasing strength of intermolecular forces. Now, in terms of flammability and the ability to burn, that's also a consequence of the fact that in these larger molecules, you have larger numbers of carbon to carbon and carbon to hydrogen bonds. Now, as we'll see in a later lesson when we look at the burning of hydrocarbon fuels, when you burn a fuel, you're breaking the bonds between the carbons and the hydrogen atoms in those fuel molecules, and then you are forming new bonds with oxygen atoms that you get from atmospheric oxygen. The more of those carbon to carbon and carbon to hydrogen bonds you have per molecule, the more work you're going to have to do to break those bonds in order to form new bonds and form your carbon dioxide and water, for example. And so typically these will be less flammable and will burn less efficiently, and typically will burn less well as fuels as a result. So all of these physical properties, and to some extent the chemical properties such as their flammability, are a consequence of the increasing intermolecular forces, increasing strength of intermolecular bonds, bonds between molecules, as you go from smaller molecules to larger molecules. So, how do we separate crude oil into its components? Well, this can be done simply in the laboratory by means of a process that we call fractional distillation. So, fractional distillation is like distillation in the sense that you are evaporating something or boiling something and then condensing it. But fractional distillation is a process of separating a liquid mixture composed of different miscible liquids, liquids that will mix with each other, into its many constituent parts through separately distilling each one of those components at its characteristic boiling and condensation points. So as we saw with the alkanes, each one will boil at a unique temperature, and the reason for this is because each one has a unique level of strength of intermolecular forces between its molecules in the liquid. Now each one will also condense from a gas back to a liquid under cooling at those temperatures. And again, that's because each one of these in the pure form has its own unique strength of intermolecular bonding. But when we mix these together into a liquid mixture, what we have is molecules of various hydrocarbons all physically combined into one mixture. So each constituent part of crude oil can be separated by what we call fractional distillation, and this makes use of the idea that each one of those components will boil and then condense at a different temperature. So you can see this in the school science laboratory when your teacher demonstrates the fractional distillation of synthetic crude oil. Now, under current health and safety regulations, your teachers will not demonstrate the fractional distillation of actual crude oil, because proper crude oil is actually highly toxic and gives off very nasty vapors. But they will do it with a synthetic crude oil mixture, as is being shown here. So you start with glass wool soaked in crude oil inside a boiling tube. The boiling tube has a thermometer attached near the end of it, which will monitor the temperature of the vapors which are coming off this as we're about to heat it. Now what you also have is a delivery tube leading from the boiling tube, which goes into a cooled boiling tube, which is in a cooled water bath. So let's take a look at how this works. So to begin with, the crude oil is heated using a Bunsen flame in the boiling tube, and it's heated up to a temperature of about 100 degrees centigrade. Now the fraction, the part of the crude oil with the lowest boiling points. Now again, the term fraction doesn't mean a specific substance. It means a group of substances that all have similar boiling points. So the fraction with the lowest boiling point will boil first and then travel as a vapor along the delivery tube and then condense as it enters this colder tube and cools down, so that it eventually will collect in this tube here. So if we start, we have increasing temperature, and eventually the fraction with the lowest boiling temperature will boil and then condense, and then we can change the tube ready to receive the next fraction. Then the temperature will increase again until eventually it will reach at the boiling point of the next highest boiling point fraction, which will condense. And then once we've condensed all of that, we can change the test tube to collect the next fraction. The temperature rises again until it reaches the boiling point of the next fraction. That fraction will boil and then condense, and we can collect it in this tube, change the tube, keep heating. The temperature again will rise until we reach the boiling point of the next fraction. And again, that fraction will boil, will condense in this cooler delivery tube, and then we'll collect in this boiling tube. We can change the tube again, and we can keep doing this until every one of the fractions has been boiled and collected separately. So this is the process of fractional distillation. It makes use of the idea that in this mixture there are fractions composed of substances with similar boiling points, which will boil at different temperatures. So one fraction will boil at a particular temperature, it will then condense, we can collect it, we can then swap out the test tube, heat it some more until we get to the boiling point of the next fraction, which will boil and condense, then we can collect that, and we can keep doing this until we've collected all of the different fractions in the crude oil and separated them out. So this is the principle of fractional distillation that we can show in the laboratory, but this is done at an enormous industrial scale worldwide in oil refineries. So in industrial fractional distillation, the mixture, which is a very complex mixture, is first heated to a temperature high enough to boil the majority of the different chemical components or fractions in the crude oil. So it's a slightly different approach which is used than the approach that we use in the laboratory. Instead of boiling each fraction separately and condensing it separately, we boil the entire mixture so that we now have a mixture of gases. That mixture of gases then rises up a device called a fractionating column, which is hotter at the bottom and cooler at the top, and each fraction will condense back to a liquid when it rises up to a level in the fractionating column where the temperature is below its condensation point or boiling point. So each fraction can then be separated and then collected in that way. So the fraction with the lowest boiling point is collected towards the top of the column where the temperature is lowest. The fraction with the next lowest boiling point is collected just below the top of the column, and so on. In this way, each fraction which makes up the crude oil can be separated and collected. So what you see here, let me just turn on my pointer. So this is an oil refinery. This column here is the fractionating column. So at the bottom, the crude oil is vaporized into a mixture of gases. That gas rises up until it reaches this level here where the temperature is slightly lower than it is at the bottom. At this temperature, the fraction with the boiling point or condensation point temperature corresponding to this temperature in the column will liquefy, will condense, and as you can see here, there's a pipe here which will then extract that liquid and take it away to be stored. The rest of the mixture of gases will then continue to rise through the column until it reaches this part of the column, which is at a lower temperature, where another fraction will condense off and be stored separately. The mixture of gases will then rise further to this cooler level here, where another fraction will be condensed and siphoned off, and so on. So this is how a fractionating column works. So let me show you an animation which illustrates how that works in a bit more depth here. So I'm going to turn on all the labels here. So the crude oil enters through this pipe as a liquid. It passes through this furnace section, which heats the crude oil to a temperature of about 400 degrees centigrade, which vaporizes the majority of the substances in this mixture. So now the majority of the crude oil has become a gaseous mixture here. The remaining components of the crude oil, which are still liquid, will be tapped off at the bottom here. Now, typically, these are the largest molecules. So here we're talking about hydrocarbon molecules more than 70 carbons. And again, the reason why these don't vaporize, even at this very high temperature, is because these are very, very large molecules with very large forces of attraction between them. And so their melting point and boiling points are higher than this 400 degrees centigrade here. Now the remaining gases will rise up this column and reach this level, which is at a slightly lower temperature. At this level, at about 340 degrees centigrade, we get the fraction which contains hydrocarbon molecules with a size of between 45 and 70 carbons. So this fraction is where you find the components of fuel oil. And as the remaining gases rise up this fractionating column, they will each condense at a level at which you find the condensation point temperatures for those fractions. And in this way, we can separate out these fractions, each of which, as you can see, has a particular use in various different industries, until you reach the top of the fractionating column, which is around room temperature. This is where you get those gases, those hydrocarbons such as methane all the way through to butane, which are all gases. And again, you can see that in this table. Methane all the way through to butane, 1 carbon to 4 carbons, these are all gases, and these are collected at the top of the fractionating column. So this fractionating column has a temperature gradient across it, from the highest temperatures at the bottom to the lowest temperatures at the top. And at specific levels along the fractionating column, the engineers will place these arrangements called bubble caps. So these bubble caps are designed to help these substances condense at their respective condensation point temperatures. So the fractionating column has a temperature gradient. It's cooler towards the top of the column. As the vapor moves up the column, each group of alkanes, each fraction, which again is a mixture of alkanes with similar condensation point temperatures, each one will cool down enough at each one of these levels to condense separately and be siphoned off separately. So each group of alkanes, each fraction, will condense within the column at a specific height, which is determined by its boiling point. The liquid alkanes are tapped off from the column in these separate fractions, and the gaseous alkanes will be separated at the top of the column. So the different fractions are then stored in very, very large tanks like the ones that you see here in this oil refinery before use. Now the fractions can be used as fuels or for industrial purposes for making a vast variety of different compounds and products. Now we're going to be looking at some of the other processes involved in producing those useful products in a later lesson. But for now, let's take a look at some of the uses of these fractions. So bitumen is used for construction and road repair. So if we look at the next fraction up, so slightly smaller molecules from 45 carbons to 70 carbons, these are the types of molecules which are typically used in fuel oil. Now, fuel oil typically is within this range, it's about 25 to 50 carbons, but there is a bit of overlap here. So fuel oil is used for very large vessels such as container ships. Then you have the lubricating oils. So again, there's some overlap here, but the lubricating oils are typically viscous oils. Now again, this goes back to what we were saying about some of these compounds and the sizes of the molecules. The larger the molecules are, the stronger the intermolecular forces between them, and so the more viscous, the thicker those liquids tend to be. Then you've got diesel oil, which is used in relatively large vehicles such as buses. And then you have kerosene, which is used as jet fuel. So this is from 10 to 16 carbons here. Then you have chemicals such as naphtha. So naphtha is not particularly useful in and of itself, but it does contain a wide variety of other useful chemicals, and it's used to produce other materials, such as in the plastics industry. Then you have petrol. So petrol is between 5 to 10 carbons, and this obviously is a very important fuel for cars and various other vehicles. And then finally you have the gases, methane, ethane, propane, and butane. Now these are used as fuels, but some of them are used for other applications as well. So here we can see the use of one of these fractions, bitumen. So every fraction from crude oil has a use. Even the heavy molecules that don't vaporize in the fractionating column are used as bitumen for surfacing of roads and pavements. Now, the majority of the world's crude oil production is now used to produce fuel to meet the world's ever-increasing demand for transport, both passenger and freight transport. So ships, planes, trains, and road vehicles, they all burn vast quantities of oil-based fuels, and the world's economy would collapse if the oil supply was to cease. Okay, everyone, that's going to do it for today's lesson. I hope that was useful to you. I'm now going to go into the Q&A session with the students that I have in attendance with me. Thanks for watching, and I'll see you in the next one. Take care.